title of the module is Kruskal's algorithm. In this module, we will be studying about the greedy technique and how it can be used to find the minimum spanning tree by using Kruskal's algorithm. We will also be studying about Prim's algorithm, that is also an algorithm used to find minimum spanning trees. In the end, we will be able to see how Kruskal's algorithm is superior to Prim's algorithm. Let us first study about the greedy technique. The greedy technique is, let us assume that you are a cashier in a bank and a customer approaches you to ask for change in the place of 100 rupees. The quickest way to do this exchange is to give them 250 rupee notes. If you had only 150 rupees notes, the next logical step is to give them 150 rupees note, 2 rupees 20 notes and 1 rupee 10 note. This is a logical strategy of making a sequence of best choices among the currently available alternatives. This approach is called greedy. The greedy approach suggests that constructing a solution through a sequence of steps, each expanding a partially constructed solution obtained so far until a complete solution to the problem is reached. The choice should be number 1, feasible, that is, it has to satisfy the problem's constraints. Number 2, it has to be locally optimal, that is, it must be the best local choice among all feasible choices available on that step. And number 3, it should be irrevocable, that is, once the choice is made, it cannot be changed on subsequent steps of the algorithm. We will be using the greedy technique to solve the problem of the minimum spanning tree. Let us recall some definitions that we have studied in the earlier modules. Definition 1. A spanning tree of a connected graph is its connected acyclic subgraph, that is, a tree that contains all the vertices of a graph. A minimum spanning tree of a weighted connected graph is its spanning tree of the smallest weight, where the weight of a tree is defined as the sum of the weights on all its edges. The minimum spanning tree problem is the problem of finding a minimum spanning tree for a given weighted connected graph. As you can see from the figure shown on the screen, we can find different spanning trees for the same graph, and the different weighted spanning trees would yield different weights at the end of the process. We have to choose the spanning tree with the minimum weight. If we were to try an exhaustive search approach to constructing a minimum spanning tree, we would face 2 serious obstacles. First, the number of spanning trees grows exponentially with the graph size. Number 2, generating all spanning trees for a given graph is not easy. In fact, it is more difficult than finding a minimum spanning tree for a weighted graph by using one of the several efficient algorithms available for this problem. In the next section, we shall see Prim's algorithm with its pseudocode, which constructs a minimum spanning tree through a sequence of expanding subtrees. A pseudocode is an algorithm in which you have written the steps in the form of a false code, and that is why it is called the pseudocode. It looks like a computer program, but it is actually not, but it can be used to create a computer program quite easily. So now we see the Prim's algorithm for constructing a minimum spanning tree. The input is a weighted connected graph G equal to V, E, where V represents the set of vertices and E represents the set of edges of the graph. The output is E suffix t or ET, the set of edges composing a minimum spanning tree of G. Let Vt be assigned as V0. The set of tree vertices can be initialized with any vertex. So, the initial vertex is initialized as V0. Et, the set is assigned phi. For I equal to 1, 2, the cardinality of V minus 1, do find a minimum weight edge E star which is equal to V star comma U star among all the edges V comma U such that V is in Vt and U is in V minus Vt. So, Vt is assigned Vt union U star and Et is assigned Et union E star. So, the loop runs from 1 to V minus 1. So, that is the number of times the for loop runs. Finally, the output return Et. The Prim's algorithm constructs a minimum spanning tree through a sequence of expanding subtrees. The initial subtree in such a sequence consists of a single vertex selected arbitrarily from the set V of the graph's vertices. On each iteration, we expand the current tree in a greedy manner by simply attaching it to the nearest vertex not in that tree. The algorithm stops after all the graph's vertices have been included in the tree being constructed. Since the algorithm expands a tree by exactly one vertex on each of its iterations, the total number of such iterations is n minus 1, where n is the number of vertices in the graph. The tree generated by the algorithm is obtained as a set of edges used for the tree expansions. There is another greedy algorithm for the minimum spanning tree problem that also always yields an optimal solution. It is named Kruskal's algorithm after Joseph Kruskal, who discovered the algorithm when he was a second-year graduate student. Kruskal's algorithm looks at a minimum spanning tree for a weighted connected graph G with vertex set V and edge set E as an acyclic subgraph with mod V minus 1, that is the cardinality of V minus 1 number of edges for which the sum of the edge weights is the smallest. Consequently, the algorithm constructs a minimum spanning tree as an expanding sequence of subgraphs which are always acyclic but are not necessarily connected on the intermediate stages of the algorithm. We shall now study the Kruskal's algorithm to find a minimum spanning tree of a graph. Let us see the theorem. The Kruskal's algorithm produces a minimum spanning tree. The proof is given as such. Let n be equal to the set of vertices, edges and the function f connecting the set of vertices and edges be an undirected network. Let h be a subgraph of the underlying graph G equal to V comma E of n, and let the function of h is equal to the summation of all E belonging to h over f of E. Let the graph n be of order p. Let T be a spanning tree of n created using Kruskal's algorithm. Then, from the size of the tree is 1 less than the order T has p minus 1 edges. Let the edges of T be ordered as E1, E2 and so on up to EP minus 1 according to the construction of the Kruskal's algorithm. Then, f of T is equal to summation over I equal to 1 to p minus 1 f of ei. Let T naught be a minimum spanning tree of n. Suppose that T naught and T are not equal, then T has one or more edges which are not in T naught. Using the ordering on the edges created above, let ei be the first edge of T not in T naught. By construction, 1 less than or equal to I less than or equal to p minus 1. Let ei be added to T naught to obtain the graph G naught. Let ei equal to ub where u comma v belonging to the vertex set are vertices of n. Then there exists a uv path p in T naught. Together with ei, this makes a cycle C in G naught. Since T contains no cycles, there must be an edge E naught of C which is not in T. Thus, the edge deletion T dash naught is equal to G naught minus E naught is also a spanning tree of n, and f of t dash naught is equal to f of t naught plus f of ei minus f of e naught, but as t naught is a minimum spanning tree, the function of t naught is less than or equal to f of t dash naught. So, f of t naught minus f dash of t naught is less than or equal to 0, but since f of t naught minus f of t dash naught is equal to f of e naught minus f of ei, it follows that f of e naught is less than or equal to f of ei. However, the way t was constructed, ei is an edge of smallest value which can be added to E1, E2 and so on up to E minus 1 without producing a cycle. Also, if E naught is added to E1, E2 and so on up to Ei minus 1, again no cycle is produced. Therefore, f of Ei is equal to f of E naught, and so f of t dash naught is equal to f of t naught. Thus, t dash naught is a minimum spanning tree which has one more edge in common with t than t naught, that is Ei. The procedure can be repeated as many times as there are edges in t naught which are not in t. Finally, the spanning tree T is arrived at, which by the above is a minimum spanning tree. Hence the result. The correctness of Kruskal's algorithm can be proved by repeating the essential steps of the proof of Prim's algorithm given in the previous module. The fact that ET is a tree in Prim's algorithm, but generally just an acyclic subgraph in Kruskal's algorithm is an obstacle that we can easily overcome. Applying Prim's and Kruskal's algorithms to the same small graph by hand may create the impression that the Prim's algorithm is simpler than the Kruskal's algorithm. This impression is wrong because on each of its iterations, Kruskal's algorithms has to check whether the addition of the next edge to the edges already selected would create a cycle. It is not difficult to see that a new cycle is created if and only if the new edge connects two vertices already connected by a path. That is, if and only if the two vertices belong to the same connected component. In the previous modules, we have already studied in detail about the Prim's algorithm, but however, let us just recall how the Prim's algorithm works so that we can compare it with how Kruskal's algorithm works. Now, for that, let us go to this graph. We have a 6 vertex graph and there are several edges here, and all these edges have weights, and some of the weights are 1, 3, 4, 5, 6, 8, etc. And now we have to use the Prim's algorithm to find the minimum spanning tree of this graph. Now, in Prim's algorithm, we usually start with the vertex. So, let us take A for in an arbitrary manner. Let us choose A. Now, A can go either two ways. The next vertex can be chosen in either two ways. You can either go to F or you can go to B. But since 3 is the minimum edge here, so it is the edge with the minimum weight, I am going to go with B. Therefore, I choose this edge and I choose this vertex. So, after doing this, now I can go from B to either C or to F. Here the edge is 1 and here it is 4, and therefore, I can go to C because that has got the edge with the minimum weight, and therefore, I am choosing C. Then after this I can go to, from C I can go to 4 to F or D, and here 4 seems to be the minimum minimum weight, and therefore I am choosing F. And finally from F I can go either this way or this way, and obviously this is the way to go because 2 is the minimum weight, and therefore E is chosen. Now there is only one way to go, only one vertex is left uncovered, and therefore I can either go like this from E to D or from F to D, and but here the weight is 8 and here the weight is 5, and therefore obvious choice is to go for this edge, and therefore I am choosing the vertex D. So, in this process I have covered, so from A to B, then B to C, then from C to F, and from F to E, and finally we backtrack and then we choose D. So, this is how we have arrived at this minimum spanning tree using the Prim's algorithm. The concept that you can see in this is that we are consequently creating a subtree. We are using the technique of greedy technique to choose consequent subtrees in such a manner that we are growing the subtrees. So, we choose one point, we are slowly growing from that point and from then the next point and so on. We will see how this technique is completely different from what Kruskal advocates. So, this is how we arrive at the minimum spanning tree for a Prim's algorithm, and in each step we are holding on to the connection of the previous vertex. So, that is the main purpose of Prim's algorithm. You slowly grow from one vertex and you slowly build on what you already have and then arrive at a minimum spanning tree. Now, we come to the most important part of this module. As the title itself suggests, we are here to learn the Kruskal's algorithm, and that is what we are going to study now. So, you can see Kruskal's algorithm for finding the minimum spanning tree. I have written the pseudocode for the minimum spanning tree algorithm using Kruskal's algorithm. So, the input is a weighted connected graph with vertex set V and edge set E, and the output is a set of edges corresponding to the minimum spanning tree with decreasing weights W of ei1, W of ei2 and so on. So, this is how the set of edges we arrive. So, the first edge is of the minimum weight, and slowly we build on that, and it is actually in a sort of an ascending order. That is why we have mentioned it like this, the weights are in ascending order. And then in the edge set is first initialized as empty set, and we have a counter as 0. The counter is initializing the set of tree edges and size. So, first we initialize k to be the number of processed edges as k, and that is also initialized as empty. So, ET represents the edge set, counter is a number to initialize the set of tree edges and size, and k is a number that initializes the number of processed edges. Now, while this counter is less than the cardinality of the set of vertices minus 1, while this is true, this statement is true, we add 1. So, k is going from k to k plus 1. So, every time the counter goes to the first vertex, the first edge, and then 1 is added to k, and then if the edge set T union ek is acyclic. So, you only have to check that the new edge that is added to the earlier edge is acyclic. They do not create a cycle. That is the only condition that you look for when you are doing this. And the edge set T ET is initialized as ET union EIK every time this is true. So, the and every time the counter goes by 1, it is added, 1 is added to the counter. So, here you can see the counter for is added, it is true until the cardinality of V minus 1, the value is greater than the counter. So, that is the only condition. The moment that this condition fails until we reach the last vertex minus 1, that is, this is actually the number of edges. So, we know that the number of vertices is m, so cardinality of V minus 1. So, until that is true, the counter keeps moving. When this is failing, the while loop ends and you are arriving at ET, which gives you the set of edges with increasing weights, and that will give you the minimum spanning tree got through the Kruskal's algorithm. Now, this is in pseudocode. The same thing, if it can be told in plain text, is that we in any graph we choose the edges. See, we do not care about the vertices anymore, we do not care if they are connected to each other anymore, if we do not care if the consequent edges are close to each other, we do not care about all of them. In Kruskal's algorithm, all we do is we use the greedy technique to subsequently choose those edges of sequential weight increase. So, if I am choosing an edge with weight 1, the next edge that I will be choosing will be the edge with weight 2, and so on and so forth. So, we no longer care whether we connect to one edge or the other. Now, I am going to demonstrate Kruskal's algorithm using this graph. This is a graph that we already used to study the Prim's algorithm and how it works. The reason I am using the same graph is that to make you understand how the Prim's algorithm and the Kruskal's algorithm work in very different ways. And so, let us go to this Kruskal's algorithm. So, you need to choose edges of weights in consequent increasing order. So, we are using the greedy technique to make the best choices in consequent order. So, here I am going to choose the edge with the minimum weight. Why am I choosing the minimum weight? Because we need the minimum spanning tree. Therefore, the least weight goes to this edge, and therefore, we are going to choose this edge, and I am going to draw this thing. So, and the next possible good choice, the next best choice would be 2, the weight 2, and it goes to this edge, and therefore, I am choosing this edge. Therefore, I have chosen already an edge of weight 1, next I am choosing an edge of weight 2. So, you can see that these two edges do not bear any kind of adjacency, there is no connection between them at all, they are very disjoint. But the only rule that you have to follow while using the Kruskal's algorithm is that there should not be any cycle. You have to make sure that the consequent edges that you choose do not form a cycle. Next, after I am choosing 2, I look around the graph and I see that there is an edge of weight 3. So, the next edge I choose is this. So, I am going for this edge. So, now that is done. The next weight is 4. Now, there are 2 edges that are having the same weight 4. So, I am going to go with this edge. So, it does not matter which one I choose. So, I am arbitrarily going ahead with this edge. Now, after choosing this, the only possibility is 5. So, after 4 there is 5. So, I am going with 5. I can actually go here also. Actually, I can go for here, but the moment I choose this edge, it immediately forms a cycle. If you can see the cycle, that beats the purpose, because we need a tree and a tree is a cyclic. Therefore, I am going for this edge and I have chosen the vertex D. So, all the vertices have been covered. So, A is covered, B covered, C is covered, F, E, D, all of them are covered, and I have got a few edges. So, I am going to draw this to show you how the minimum spanning tree looks like. So, A, B, this is weight 1, weight 3, 4, 5, 2. So, this is the minimum spanning tree we have arrived at using the Kruskal's algorithm, and throughout the process you must have noticed that we are going as disjoint edges only. I am going to do a comparison of both the Prim's algorithm and Kruskal's algorithm. You can see that the Prim's algorithm is efficient in some ways and the Kruskal's algorithm is efficient in some other ways. You can see that the minimum spanning tree that we arrived using the Prim's algorithm is quite similar to the minimum spanning tree that we arrived at from the Kruskal's algorithm. Both the weights are, if you add all these weights, so 3 plus 1 plus 4 plus 5 plus 2, that is also 15, and the same way for Kruskal's algorithm also, if you are going to add all the edge weights, it is also coming up to 15. So, why do we say that Kruskal's algorithm is better in some ways is that when you talk about a very large network, when you talk about a very extremely large network or a parallel network or all that, when the underlying concept is a graph, but you talk about a huge network, massively parallel networks and all that, Kruskal's algorithm is much more efficient because we are consequently choosing edges of the least weight or of consequent weight increase. Therefore, here although we might get disjoint edges and edges which are no longer adjacent to each other, the end result is still a minimum spanning tree that spans all the vertices of the graph. Therefore, for very large graphs, Kruskal's algorithm is very good, but in smaller graphs the Prim's algorithm is quite efficient because you start from one point and slowly build on it and create subgraphs, subtrees and all that, and you slowly build upon that and you arrive at a minimum spanning tree. Each is useful in its own way, and therefore, that completes our study for this module, and we have now compared two different algorithms to find the same minimum spanning tree. Conclusion: in this module we studied about Kruskal's algorithm. We studied the pseudocode of Prim's algorithm and Kruskal's algorithm. We applied both the algorithms to the same graph and we tried to understand how they behave very differently but still arrive at the same minimum spanning tree. Please do the quiz and the assignment in this module because we learn by doing. Thank you.